My children, my African, welcome to the channel, guys. On this lesson, we're going to prepare for your exam now. So we're working on paper 2. And I think in past of my lesson, we never talked about questions where we have graphs like this. And I was like, you know what? Let me start with help you guys how to answer this type of questions, how to collect all these marks on this 6.1. So 6.1 is based on this graph. Okay, so now let's just start with the lesson. If this is your first time watching the lesson, please make sure that you join the family, subscribe to the channel, and I'll definitely massify you and show you how to collect this ismath. Okay, so the 6.1, the reaction of carbon monoxide gas, which is CO, with an oxygen gas, O2, it's investigated. The reaction reaches equilibrium in a closed container at a constant temperature. That's what you are given according to the balance equation. Okay, so before I go to some of the question, let me quickly explain this concept. Ladies and gents, first thing first, look at the double arrow there. Remember, you see this double arrow? It tells you that the reaction is reversible, meaning that the forward reaction, you see this delta H that is given. The delta H is exothermic, right? Because it's negative. That's exothermic. You see this exothermic is for the forward reaction. So the forward reaction will favor exothermic and the reverse reaction will favor endothermic. This is what you need to first understand. So let's continue. Changes to condition of equilibrium are made at different times. The graph shows the result obtained X, Y, and Z. Represent the gas in the above reaction. Guys, don't be afraid when you see this type of graphs. I'll definitely move with you step by step. Let's start with the first question where they want you to define chemical equilibrium. So we say that chemical equilibrium is a dynamic state. So this is a dynamic. See now? Okay, that's a dynamic state. It's a dynamic state in a closed system where the rate, you will have the rate of the forward reaction. Okay, the rate of the forward reaction, it will be equal to the rate of the reverse reaction. The reason I'm writing this down, guys, is because maybe someone is writing tomorrow and they're watching the lesson today, then they won't forget this definition when they sit on an exam paper tomorrow. Okay, so now, first thing first, you need to understand the graph. Okay, so we said the forward reaction is exothermic exothermic reaction. So this is exothermic. Right, let's answer the following question. At T1, okay, I can see T1, this is my T1 here. They said that oxygen gas was added to the container. Write down the letter that represents O2, choose from X, Y, or Z. At T1, we add oxygen. So remember, when we add oxygen, oxygen is on our reactants. So what happens when a substance is added? That's what you need to ask yourself. So we said that the concentration of that substance, it will increase instantly, vertically jump. We're going to have what we call a vertical jump. Okay, please make sure that you note this down. When you add a substance, the concentration of that substance, it increases instantly, meaning there is a vertical jump. At T1, only X that shows an immediate increase. Look at X. Is the one that shows an immediate increase because this is your T1 for X, this is your T1 for Y, and this is for Z. you're gonna look for the one that has a immediate jump. I'm not sure if we have those learners who trade forex while you are still a student. If the market, I'm sorry for saying this, if the market closes on Friday, when the market, if it closes here, and then when the market opens on Monday, you'll find that it jumped to that one because of whatever that is happening during the weekend. That's what we call the instantly increase. So you look for the one that has the vertical one. So this tells you that the correct answer to answer this one, the answer is X. Right. At T2, the pressure is adjusted by changing the volume of the container. Was the pressure increased or decreased? Let's go and indicate that T2, then we'll take it from there. At T2, so this is my T2. This is what is happening for Z. From that point, this is for Y. And from that point, this is for X. Okay, so at T2, the pressure is adjusted by changing the volume of the container. We need to understand if the pressure was increased or decreased. So all of them, all of these three, let's observe at T2. All three gases, they show an instant decrease. X decreased, Y decreased, and we have what? We have Z that is also decreased. All of them, they decreased in concentration because this is the concentration. So now, this means that since all of them are decreasing, so to answer that 6.1.2, we go, oh, not 6.1.2, 6.1.3. All of them are decreased. What is that telling you? The volume was increased. So the volume was increased. Okay, so since the volume was increased, when the volume increased, the particles will spread out. When the particles spread out, the concentration decreases. So this will decrease the concentration, as you can see from the graph. No need for me to write this down. So a decrease in concentration tells you that the pressure was decreased. So the correct answer is decrease. Please don't do guesswork when you get in an exam. Say, today I'll go with decrease. I feel decrease. You might be lucky sometimes. You might lose a mark and choose increased. 6.1.4. Give a reason for the answer to 6.1.3. Now they want a reason. You see? So when they want a reason, you'll say the pressure. I'm just going to give you the easiest one. The pressure is inversely proportional to volume. The pressure is inversely proportional to volume. Meaning that increasing volume, V for volume, will cause P to decrease, the pressure to decrease. Good. When you do 6.1.3 and you're like, I'll go with decrease, you are lucky. That's the correct one. But what about 6.1.4? Since you don't understand what's going on, you see, you're going to lose a mark. Make sure that you understand the concept. Or you can say at T2, the concentration of all gases decrease immediately, showing that the volume is increased and therefore the pressure is decreased. Guys, when the concentration decreased, this tells you that the volume was increased. So a decrease in concentration, it means the pressure was decreased. Okay, 6.1.5. Write down the name or the formula of the gas that is represented by letter Z. Let's go and see Z. They want us to name the name, write down the name or the formula of the gas that was represented by letter Z, and I can see Z there. Okay, so let me look at this. Let me look at this. At T1, they said O2 was added. The equilibrium shift right to use up what? The equilibrium shifted to the right to use up that O2. So the forward reaction, this tells you that, remember, the forward reaction, it's, if we do this, the forward reaction does 2 CO plus O2, they form 2CO2. So the forward reaction is favored, right? The forward reaction is favored because we can see that after that, whatever that was added, the CO decreased. So this CO, I'm going to indicate that with a different marker so that we can be on the same page. The CO decreased. You can see the CO. Oh, wait. Look at this. After this one is decreasing, which was the O2. So the O2 decreased, and then this one is the same. This one should be the same. Let's not say phase. It should be on the same side as the CO. Come on, as the O2. Since the O2 is decreasing, whatever that is decreasing after that change, it should be at the same side. So this tells you that the CO is also decreasing. So this will be the CO. Because the one that will do an opposite, it should be on the other side of that O2, which is the CO2. So this should be the product, which is the CO2. That's how you determine what is what. Already we know that X is O2. So the one that do whatever that O2 do, they should be on the same side, which are your reactants. They should be on the same side as that one, which is what? The CO. So the correct answer for this one is the CO. The correct answer for that one is CO. Right. And then after T1, you can look at this. After T1, we can see that X it decreases, and then the Y increase, the product are formed, and then the Z decrease, meaning that the reactants are consumed. Thus, Z must be that CO. Okay, carbon monoxide. Okay, next one. Give a reason for the answers. Come on. The one has to give a reason. Okay, so the reason is that when O2 is added, we know that it's added at T1. Okay, and then the equilibrium shift to the right. Therefore, Z decrease also. Right, showing that Z is reactant. Already we know that O2 is reactant, so the other one should be Z, which is CO2. It's reactant being used up. Right, so carbon monoxide is a reactant in the forward reaction. Therefore, you can tell them that the carbon monoxide is the reactant in the forward reaction. And that's it for that one. I'm just going to move to the next question. What change in temperature is made at T3? Choose between increase or decrease. Then they want you to use the Hartley's principle to explain that answer. Okay, let's look at T3. What temperature is being introduced at T3? Okay, so remember, let's observe what is going on here. At this point, the X decrease. I'm going to write D for decrease. At this point, we can see that the Y increase, I for increase. At this point, the Z will do the same, whatever D, whatever X is doing, which is decrease. So this means equilibrium shift to the right. Look at this. More products are formed. Equilibrium shift to the right. Because the equilibrium, it shifts to what? To the right. Why? Because we have more products that are formed. Okay, So when you have this, I want you to use delta H. Remember, delta H is less than 0, okay? So since delta H is less than 0, the forward reaction, that's exothermic. You can see that's what we determined when we started the session. So what happens? Remember, lowering temperature it forward, if the temperature, let's write this down next. Someone might need this. So if the temperature is decreased, so a decrease in temperature will favor what? A decrease in temperature, it favors endothermic reaction. I'm sorry, exothermic reaction. Okay, that's what I need you to understand for now. So therefore, the equilibrium will shift to the right. So to complete this answer, when the they say that what change in the temperature is made at T3? Choose between increase or decrease. Right. So now we know that if we decrease temperature, if you decrease temperature, we're going to favor exothermic reaction. So since we favor exothermic reaction, what is this telling you? The forward reaction will be favored if we decrease temperature. So look at this. We are creating, at T3, we are creating more products, meaning that creating more products favors the forward reaction, which is exothermic. Exothermic, it goes with a decrease in temperature. So more products are formed, the forward reaction is favored. Therefore, the correct answer is the temperature is decreased because more products are formed at T3, meaning that the exothermic reaction is favored. We're going to use that to explain this according to Le Chatelet's principle. My children, my Africa, remember, according to Le Chatelet's principle, when the temperature is decreased, the system will oppose the change by favoring the exothermic reaction. Since the exothermic reaction is, since the forward reaction is exothermic, the equilibrium will shift to the right to produce more heat. So as a result, the concentration of the CO2 will increase and the concentration of the CO and the O2 will decrease. According to Le Chatelet's principle, okay, according to Le Chatelet's principle, we say that when temperature is decreased, what will happen? The system opposes the change, which is the stress cost, the change by what? By favoring exothermic reaction. And then, since the forward reaction is exothermic, the equilibrium shifts to the right it shifts to the right. And why? To produce more heat. That's why we are having more products being formed. As a result, therefore, the concentration, let me just use this for concentration. Remember, big brackets means concentration increases, and the concentration of the CO and the concentration of the O2 decreases. And that's it for this one. That's how you should answer this question. And that's it for this one. I hope you guys are having so much fun on this one. This was easy, right? This was easy, very, very easy question. I just wanted to show you guys how to collect those marks. Né? Okay, great. So let's look at this question. So this has to do with chemical equilibrium. Let's see what we have on the first question. The reaction between a steam and a chlorine gas, it reaches equilibrium in a closed container according to the following balanced equation. So this is what we call an isolated, no, this is a closed system. It's not an open system, okay? So we are given a chemical reaction and they say that delta H is positive 113, okay, kilojoules. And now the first question they asking you is this reaction exothermic or endothermic? They want you to give a reason for your answer. So let me quickly explain how this works. Remember, in exothermic reaction, when we say exothermic, the heat is released to the surrounding, right? So this tells you that delta H must be less than 0, meaning that the delta H, it must be negative, and for endothermic, delta H, it must be greater than 0. When we look at the change in enthalpy that is given, it is positive. This is just an easy 2 marks. It is positive, meaning this is endothermic reaction. So the correct answer, it's endothermic. So I'm going to take endothermic as my answer, then I need to give a reason. So the reason, you can just tell the marker that the value of your delta H is positive, and you'll definitely get 2 marks for that. 1 mark for endothermic, 1 mark for the reason. So a positive delta H, it means that the heat is absorbed from the surrounding during the forward reaction. So yeah, you can just give it as easy as like this. There will be 2 mark allocation for that. Next question, they say the graph below, not drawn to scale, shows how the amount of products present in the container change with time at a specific temperature. The volume of the container is 5 decimeter cube. Let's quickly look at what we have on our products, because this graph is only for the products. Look at the products. This is hydrochloric acid and oxygen, and we can see that both of them, so the hydrochloric acid, it starts with the amount and the number of moles as 1, then it decreases. Same applies to what? Same applies to the number of moles of your oxygen. It starts at 0.3, then it also decreases. Now, which reaction is favored? Choose from forward or the reverse, and they want you to give a reason for your answer. Okay, so you know what I'm going to do? What I'm going to do, we can see that if I have, let me quickly explain this one. If you look at this double arrow here, the double arrow, it tells you that the reaction is reversible, meaning that if the forward reaction is favored, this arrow, the one on top, the arrow for the one on top on that double arrow is for forward reaction. Then the one on bottom, it will be for the reverse. What I need you to understand is that if the reactants, remember these are your reactants, then we form the products. And these are, so this tells you that if the number of reactants are decreasing, the forward reaction is favored. And if the number of the products are the ones that are decreasing, the reverse reaction is favored. Okay, because when you look at the graph, the products are the ones that are decreasing. So the products are decreasing. And we are saying that if the products are decreasing, therefore the reverse is the one that is favored, because we are using the product to create more reactants. So the reverse reaction is favored. Okay, 100%. So now, when they ask us to choose from forward or reverse, which reaction is favored, we're saying that the correct answer is reverse. And what will be the reason? The reason is that, remember, on the graph, HCl is decreasing, O2 is decreasing. Those are our products. Since the amount of products are decreasing with time, the products are being converted back into reactants. Therefore, the reason will be amount of products decrease with time. The amount of products, they decrease with time. Right. So the products are being, you can definitely tell the marker that the products are being converted back to the reactants. Okay. How do the rates of the forward and the reverse reaction compare at T3? So let's quickly go to T3. So if you look at T3, you can see that both the rate and the reverse. So you look at that T3, this is what we call at equilibrium. So equilibrium is being reached at equilibrium. Right. At equilibrium, what we know about at equilibrium is that we know that the rate of the forward is equals to the rate of reverse. So the correct answer is equal to, and they don't want you to give a reason for that. So we're just gonna say the correct answer, it's equal. No reason, because at equilibrium, we're saying that the rate of the forward reaction, FR for forward reaction, is equal to the rate of the reverse reaction, RR for reverse, FR for forward reaction. There's no there's no reason for that. Right. So maybe they can say, give a reason for answer why you're saying the rate of the forward is equal to the rate of the reverse. The reason is that at T3 the reaction reaches equilibrium. Wow, let's go to one of the most interesting questions where we have to calculate the equilibrium constant for this reaction. And at this temperature, if there was initially 5 grams of water. Okay, so look at this. They say there is initially 5 grams of water, which is my H2O, and 5 grams of chlorine. Okay, so 5 grams of water and 5 grams of chlorine, which is my Cl2. So I'm given the initial mass. Okay, so first thing first, is this given equation balanced? This is where I want you to start. You check if the equation is balanced. So if I look at this, I have 2 hydrogen here, and then when I check, oh, there's 4 on the reactants, because it's 2 times 2, there's 4 of them. And then when we go to the other side, there's also 4. Oxygen, there's 2. And when you go to the other side, there's 2. Chlorine, there's 4. On the other side, there's 4. Then this equation is balanced. Okay, please make sure that you verify that first. Okay, so now this is where I'm going to first start. I'm going to take this step by step. Okay, so first thing first, I want us to start by writing the balanced equation down. Let's bring our balanced equation down here and see what we have. So the balanced equation, that was 2H2O, which is in gas state, and then this react with 2 of chlorine, and then the reaction is reversible, and then we have 4 HCl. Okay, so now look at this. No stories for Fetu, just marks. I don't like to tell you guys stories. I don't like making jokes. Let's focus on the work. Okay, let's focus on the work. Very, very important, because what we are going to do now, very important. Look at the mark allocation. Can you solve this question, or should we double the mark and give it to the next person? So first thing first, you're going to write down your mole ratio. Okay, you're going to write down your what we call your mole ratio. Okay, so the ratio for this equation, the ratio for H2O, the ratio is 2, and then for Cl, that's 2, and then for HCl, that's 4, and the last one, that's 1, because we take the number that is in front of those molecules. So you just have to take those numbers, then your ratio will be 1. Is for H2O, the ratio is 2, and we have for Cl2, the ratio is just 2, and for HCl, the ratio is 4, and then for O2, we have the ratio is 1. This is where you start. You write the ratio. Ladies and gents, we're going to use the what we call the RICE method. So the RICE method goes like this. We have the 1 for the ratio, and then let me just put it here, the ratio, and then we'll go to I, which is the initial mole initially, then we go to C, which will be the change in mole, and then the last one, it's equilibrium. Okay, so we're done with the ratio. Now let's focus on calculating what I for initial. Calculate the initial moles of reactants. Okay, so we take all the reactants, we're going to calculate the initial moles of what? Of your reactants. Okay, so look at this. How many reactants do we have? This is my reactants. Okay, so let's start with water. Let's start with H2O. Let's calculate the number of moles. And the formula that we're going to use, it's N, it's equal to the mass over the molar mass. Okay, the mass over the molar mass. And initially from the statement, we're given the mass of water as 5 and also the mass of chlorine as 5. We just have to use the periodic table to calculate the molar mass. Okay, so now when I look at this, I need to find the molar mass of this. Okay, so now I'll go to my periodic table and look at the molar mass for H. When we go to the periodic table, you can see that the molar mass for H is just 1, because we take the number that you find below that H, which is 1, and then we need for 2. Remember, it was H2O. So for O, that's 16. So please keep those numbers in mind. We're going to use those now. So the molar mass of H2O That's equals to, you take that 1, you multiply that by the 2, which is that subscript number, and then you add the 1 for oxygen, which is just 16, which will give us the molar mole for H2O to be 1 times 2, that's 2 plus 16, that's 18 grams per mole. So that's your molar mass for hydrogen. If we do the substitution, initially we had 5 grams over the molar mass, which is 18. So this is just 5 divided by 18. You punch this on the calculator and see what you get. Okay, so I'm just going to quickly put this one on the calculator. This gives us 18, which is multiplied by the 5 is divided by 18. And this gives us 0. Let me just fix my calculator, because I don't want this to round off my answer. If it keeps on rounding my answer, this will be, I won't get the answer that I'm looking for because it keeps on rounding off my answer. Okay, let me just use a different calculator on my side. 5 divided by 18, that's 0.27. So the whatever number, that the line that you see on top, it tells you that the 7 is recurring. So when I round it off, I get my number of moles for water is 0.28. So this will be 0.28 mole. Right. So this was the first thing. You calculate the initial moles of the reactants. We're going to apply the same method to find the initial moles of what? Of chloride. Okay, so we use the same formula. The number of moles is equal to the mass over the molar mass. We need to first find that molar mass for chlorine, the molar mass for Cl2. So let's just go to chlorine. On the periodic table, we take the number that we get. Where's chlorine? Okay, this is 35.5. But remember, that should be multiplied by 2. Guys, this is nice stuff, né? So this number here, the 0. We're going to take the 35.5, which is multiplied by 2. Therefore, this will give us the number of moles. What do we get if we punch that on the calculator? 35.5 multiplied by 2, that's 71. So the number of moles, that is equal to 71. So this is 71 grams, not number of moles, but the molar mass. So remember, this was also 5. We divide that by 71. So whatever that you get is going to be the number of moles of chlorine. 5 divided by answer, that is 0.07. If I round it off, 0.07. Okay, 0.07 mole. Okay, so now remember, we just did what we call a massive calculations here, and we have the number of moles of H2O initially to be 0.28. This is very important. I'm just going to put this inside, and then the number of moles of Cl2, which we just got as 0.07 mole. This is also important. Just going to put it inside the box. Let me quickly go back and check this one. Okay, we have the initial number of moles. So now we're going to read initial product amount from the graph. Okay, because when you are given the graph, if you look at the graph, this tells you that at T0, this is where the reaction starts, right? The reaction will start where? At T0. At this guy, this is where the reaction starts. So this tells you that initially we started with HCl of 1.0, and initially we started with 0.3 of O2. So I'm going to rate those number of moles and write them down here, because we're definitely going to need those number of moles. Okay, so I'm going to call this you're going to rate initial number of moles let's just say number of products amount from the graph. So when we do that, we find that the number of moles for HCl, that was 1.0, and the number of moles for oxygen, that was 0.3. So let's move to the next step. Now we know initially for all these product molecules that you see there, we're going to move to the next step. Right. Step number 2, I need you to determine the change in moles, because remember, we're done with initial, we go to C, which is the change in moles. So we're going to determine, you see now, the change, determine the change in moles. Guys, I know we are taking so much time on this question. I just want you to take this step by step, okay? Right. So this is what we call the love for the subject. You need to make sure that you love the subject. Now, if you want to master this subject, just love the subject. So look at this. From the graph, look at O2. If we analyze this from the graph, the change in mole, O2 decreased from 0.3 to 0.1. I'm not sure if you can read that from the graph. The O2 start with 0.3, then it decreased. At this point, it start reaching equilibrium. So it decreased what? 0.3 to 0.1. We need to calculate that change in mole. So meaning that if we find the change in mole for O2, it will be the change in mole. We need to take the final amount, which is 0.1. You subtract the initial amount, which is 0.3. Therefore, the change in mole for O2 is just negative 0.2. Right, I'm just going to write this down so that I don't forget. This is my change in mole. So the change in mole, the change in O2, that's negative 0.2. Why do we need this? Why do we need the change in mole? Because we're going to use what we call the stoichiometric ratio to find other change in moles. Remember, the ratio is 2 is to 2 is to 4 is to 1. This is what we have from the balanced equation. So if O2 changes by minus 0.2, therefore, if O2 changes by this, what will the HCl change with? The HCl, what will the HCl change with? So you're going to first, remember this is for H2O, this is for Cl2, this is for H2O, HCl, and this is for O2. Okay, so the HCl will change with 4. You multiply the 4 by negative 0.2, which gives us negative 0.8. You do the same for the H2O. Then you're going to have 2 into, remember, if you look at this, if you look at this, always your products, which are these two guys, they will be positive, and then your what is this? Your reactants will be positive and your product will be negative. So when you sub in inside that formula, you don't multiply by negative 0.2. Since this is a product, since this is a reactant, we need to multiply by positive 0.2. If you don't understand this, don't worry. This will make sense now when I complete my table. So this will be positive 0.4, and then I have another reactant, which is Cl2, and then this will be 2 into, we don't multiply by negative 0.2, but by positive 0.2. This will be positive 0.4. Okay, so now if you want, you can just start doing your table, or you can just continue finding other things that you will need for your table, because remember, now you have the change. We are at this step and we have the change for all these molecules. The last part is calculating what? Is calculating the equilibrium moles. This is the E is for equilibrium moles. That is the last part. You calculate the equilibrium moles. Don't worry, we're definitely going to do the table now, right? So the next part, we're going to calculate the equilibrium moles. Okay, so first thing first, I'm gonna start with H2O, which is my reactant. You take the initial. Remember, the initial we started with 0.28. Then you're going to add that 0.14. Right, you're going to add 0.4. And then the answer that you get is going to be your initial. No, the equilibrium mole, that's 0.68 mole. Okay, you do the same for Cl2, which is your reactants. You take that what was for Cl2? Initially, we started with 0.07. So I'm going to put my 0.07 here. You add the 0.4, which is, what is that? We get this, if we add the 2, we get 0.47 mole. Ladies and gents, those were for your reactants. That was for your reactants. So now, for your product, you're going to, instead of adding, you subtract. You take the initial one, the one that we started with. If you look at this, if we can start with the HCl, you go to the graph. We know that initially, even if you don't go to the graph, we have our readings here. Initially for HCl, that was 1. You take the 1, we move it down here. So for this one, it's going to be, you take that 1, you're going to minus, you see this 0.8, because when you add the 2, we know that the change in mole, it was negative. That's why we're going to put the negative 0.8. That's why we are subtracting. Then for the O2, we initially started with 0.3. Then we're going to minus that 0.2. Okay, then the answer for this one is just a massive 0.20 mole. And then for this one, we just get a massive 0.10 mole. Okay, so I'm just gonna try and highlight these answers. So this is the number of moles at equilibrium, number of moles at equilibrium, number of moles at equilibrium, number of moles at equilibrium. Let's quickly do our graph. You know what I'm going to do? Hopefully when I do the graph, everything will start making sense now. Ne? Remember, on the graph, we said we're going to start with the ratio, and then we're going to have the initial mole, and then we said we're going to have the change in mole, and then we're going to have the equilibrium mole. Right. So now we have H2O and Cl2 as our products and reactants. And then we have HCl and the O2 as our, what is this? Products. Right. Okay. I'm just going to try and complete my table here. I'm just going to try and complete this table. Okay. So look at this table. Look at what I'm going to do. We said the ratio is 2, 2, 4, and 1. 2, 2, 4, and 1. And then initially, I'm just going to put what we started with. For H2O, it was 0.28. And then this was 0.07. And then this was 1 from the graph. And this was 0.3. So these two, the 1 and 0.3, they're coming from the graph. So now, when you've managed to get this so far, you have a 1 mark for the 0.28 because you did calculations on that. 1 mark for the 0.07, and then this 2, that was an easy thing to do because you just read this from the graph. There's another 1 mark. 1 mark for both of these two values. So I think you guys understand where all this information is coming from. Right. Let's go and continue putting our change in mole. So the change in mole, the change in mole, we started with what? We got the change in mole as positive 0.4, which one, this one was also positive 0.4. So now this one was negative 0.8, and then this one was negative 0.2. Then now the last part is equilibrium. This one was 0.68, this one was 0.47, this one was 0.2, and the last one was 0.1. That is what we got from this. You see, this were the change in moles. For H2, 0.68, 0.47, and then 0.2, 0.1. And that's it for this one. So I'm going to add the last part, which is something that we're going to need to calculate our KC. So far, when you look at this, they will give you 1 mark for this row here, which is the ratio. We definitely used the ratio to find those numbers. There's a mark for that. And then now the last part is calculating the concentration at equilibrium. And the formula for concentration, C is equal to the number of moles at equilibrium divided by the volume. You'll go back to your statement, check if you were not given, the volume. And I think the volume, it was given, there's the volume at 5 decimeter cube. So we definitely have the volume, which is 5 decimeter cube. So C, the volume is equal to 5 decimeter cube. Okay, so let's just do some substitutions here. Okay, let's see what we can get from this one. So when I substitute the number of moles, you take that 0.68, you take the number of moles at equilibrium, you divide that by 5. The answer that you get, it will be the concentration at equilibrium. Punch this on the calculator. This is 0.136. Then we move to the next one, 0.47. You take the 0.47, you divide that by 5. We get, let me quickly do this one. This is 0.094. Okay, it's 0.47 divided by 5. I just want to confirm my work. Okay, the next one is 0.2 divided by 5. Divided by 5, that's 0.04. And then the last one, we take the 0.1 divided by 5, that's 0.02. 0.02. So I know that these values are the most important values. This is the concentration at equilibrium, right? So this will be my concentration at equilibrium. Remember, by finding this, there's another mark for that. There's definitely a mark for finding all this. So there's another mark for that block, 1 mark for all those number of the concentration at equilibrium. Let's keep moving. So remember, when you find KC, we say that KC, okay, let me quickly do this. So when I write this down, I don't understand why this keeps giving me problems. Okay, let me. Okay, I think we all agree. Okay, I think everyone can agree that KC, I don't understand what's going on, but let me just fix this issue. Okay, so I'm very sorry about that, but the issue is now fixed. Okay, so I think everyone agrees with me that the formula for KC, we need to take the concentration of the product, which was HCl, but please remember we need to put the exponent on top. The exponent is the ratio. Whatever number that was in front of that HCl, you put it here on top. Okay, we're gonna put the 4 there on top, and this is multiplied by the oxygen, which it's O2. So the number was 1, we just leave it like that. This is divided by the reactants, the concentration of the reactants. Then there's H2, the H2O, and then this was 3 part 2 because the ratio for that was 2. Same applies to the chlorine. The ratio was 2. So this will be Cl, then we put the 2 on top. Remember, there's a mark for this formula. By doing this, you will definitely have another mark. Remember, the most important thing is to show these big brackets. These big brackets, these are for concentration. So when I write something like this, I'm just saying the concentration of O2. Please make sure that you put it like this in your exam. So therefore, you just have to substitute what you have. Your Kc, it's equals to HCl, that was 0.04. 0.04, that's for HCl to the power 4. And then 0.02, that was for H2. Close the bracket, divide everything by the 0.136 squared into 0.094, and this is squared. Let's see what is Kc equals to. So now for the correct substitution, you have another mark. For the correct substitution for that, there's another mark for that, and they'll definitely give you a mark for the final answer. Okay, I'm just gonna, let me quickly, because I need us to do this one on the calculator. We have 0.04, which is squared. Make sure that after putting the square, you're gonna say multiply, because if you just use brackets, you might get an error, and then you'll feel like whatever that you did here is wrong. 0.136, close the bracket, squared, and then you multiply this by 0.094, which is also squared. So putting this on the calculator, I just want to check, because I see here on top this is 2, which should be 4. So I think it's very important that you also verify whatever that you have there before you submit your answer. So we can see that this is 3. If you round this off, that's 0.00. How many zeros? They should 4 zeros, because it's times 10 to the power minus 4, 3. So if I don't want to write this in scientific notation, this will be, the Kc will be 0. You see, 10 to the power minus 4 tells you that you have 4 zeros. Then we're going to put the 3 after those 4 zeros. So the final answer for this Kc, it will be 0.0003. That's your KC. No SI unit for KC. Wow, that was a very long one. And I'm happy with all the steps that we did to collect this. Let me just quickly confirm here. 1, 2, 3, 4, 5, 6, 7, 8. Where's the other one mark? Where's the other one mark? Oh, there's a mark for after the ratio, there's a mark for finding this block. This is where the other mark is for this block. I just forgot that one. Okay, there's another mark for that. So that will be 1, 2, 3, 4, 5. And then we should have 400%. And that's it for this one. Guys, I don't want to waste any time. If you don't understand what we did, please try to take this step by step. Take it step by step. I'm just gonna try and open the question paper again. Okay, there it is. Let's look at this now. Now that we have the 1 mark, let's try and collect this remaining 6 marks. So on 6.3, the pressure is now increased. How will this change affect the value of the equilibrium constant? Remember, guys, there's only one factor that affects KC. Ne? So they say that we are increasing the pressure. How will this change the value of the KC? The value of the KC will remain the same because only temperature affects KC. So the answer for this one, give a reason, only temperature can affect KC. And that's it for this one. 6.4, the last question. Wow, I'm so relieved that we're doing the last question. Let's dive into that one without wasting any time. The reaction is repeated with a catalyst. Draw a potential energy diagram for this reaction and indicate the non-catalyst reaction and the catalyzed reaction on the graph. Ladies and gents, remember we talked about, I'm just going to try and squeeze my graph here. Remember, we said that this graph is endothermic reaction. So if the graph is endothermic reaction, delta H is greater than 0. If delta H is greater than 0, this tells you that the products are greater than the reactants. So on top here, I'm going to have my products. This is where, and on bottom here, that's where I'm going to have my reactants. So my graph should start somewhere here and then go up like this, and it should come and end at this point, the same level as that point. Okay, right. So then these are your products and these are your reactants. So I'm going to call this graph B is the non-catalyzed. So I'm going to call that graph B. Let's use a different marker to draw the second graph, and definitely we should collect that 4 marks. Okay, so remember this part here is what we call the potential energy. And then this will be the cause of reaction. So remember, when you add a catalyst, the catalyzed one will have a lower peak. So if this is your activation energy, the catalyzed one will reduce the activation energy, but the number of the reactants and the product should remain the same. So if I do it like this, it's almost wrong. It should go same direction as that one, but when it got like that, it should create a new activation energy. You see, the blue one, that will be the graph of A, the one that is catalyzed. It will have a lower peak, but the same amount will be produced. We're going to start with the same amount. And ladies and gents, that's it for this question. This was a very, very long question because of that mark allocation. So if you feel like we took our time working on this one, I'm very sorry, but I think this is for the best. Right, this is for the best, and now we're gonna see what we do on the next question. Okay, I want us to look at this question 7. So on this one, it's acid and base. So let's quickly work on this one. Sulfuric acid, it's a diprotic acid. What do you remember from the word diprotic acid? If we said an acid, it's a diprotic. So remember, a diprotic acid can donate 2 protons, the H plus ion per molecule. Okay, so I'll definitely give you examples because I can see on 7.1.2 they want you to give the reason why sulfuric acid is referred to as a diprotic acid. First question, define the term acid in terms of Arrhenius theory. So according to Arrhenius definition, acid is a substance that it's a substance that produces the H plus ions. Okay, let's say the H plus ions. If you don't want to say, so when we say produce is the same way of saying, or you can say it increase the concentration of the H plus ions in water. That's the definition according to Arrhenius theory. So give a reason why sulfuric acid. Remember sulfuric acid, it's H2 SO4. So if you look at this H2SO4, the sulfuric acid, it's a diprotic acid because this hydrogen, it will give away these 2 hydrogen. So meaning that it will give away 2 of those H plus and will be left with SO4. So since it gave away the 2 of them, the ion will be 2 minus. So when you see this type of problem, just know that this is what we call a diprotic. A diprotic, you will see them having H2 or more than that. So this is what we call diprotic acid. Right, a substance that can donate 2 or more, 2 protons, not 2 or more, diprotic, 2, just 2 per molecule. So it can donate or release 2 of hydrogen ions per molecule. Let's go to the give a reason why. Oh, let me quickly write the reason down. Okay, so the reason for this one is going to be, okay, so guys, you can see how easy it is to pass the physics paper net. So I just wish you guys all the best on your upcoming exam. So now this one, it can donate 2 protons. Wow, imagine you are watching the lesson today, né? And they ask you this question in an exam tomorrow. You are watching the lesson today and you get this on your exam tomorrow. I don't think you'll get it wrong because there's no way you can forget this. If I tell you this today and you get it tomorrow on your exam, please make sure that you pay attention to that. A hydrogen carbonate ion, it can act as both an acid and a base. So the underlying weight, if something can act as an acid and a base, we call that an ampholyte. So it reacts with water according to the following balanced equation. We can see that. So the hydrogen carbonate, that's the hydrogen carbonate. So this is your hydrogen carbonate. So now they say write down one weight for the underlying phrase above. We call that an ampholyte. So remember, in an exam, they might say define what is an ampholyte. An ampholyte is a substance that can act as both an acid and a base. If they say define, you're going to say a substance, then you write this underlined sentence. A substance that can act as a both acid and a base. Okay, so copy the equation above and indicate the conjugate acid base pair. So guys, I'm just gonna try and work it out here. So let me analyze this step by step on the board. So I'm going to look at this. First thing first, you need to identify, the one as to identify the conjugate acid base pair. Number one, start by identify the proton transfer. Look at the substance that, or the molecule that lose H plus. Okay, and how are you going to find that? Look at this. The water start with H2 and then it loses the H, it becomes OH minus. So these two guys, they will go together. So now remember, so in order for you to understand which one will be an acid, which one will be the conjugate base, this is what you're going to do. We have the water, which is H2O. It loses the H plus and then it becomes the OH minus. Wow. So the H2O, this is your acid, because remember, acid is what we call a proton donor. Okay, so the one that gives away an acid is a proton donor. Then now look at this. Whenever you remove a H plus, when you remove an H plus, you create what we call a conjugate base. I'm not sure if this makes sense. So this tells you that this will be my acid and this will be my base. Okay, so these two guys, they will go together, but you need to understand which one it's an acid, which one it's a conjugate base. Remember, acid is the one that donates the hydrogen ion, which is this part, the hydrogen ion, the one that gives away the H plus. Okay, so we know that one. Then when you remove, you see, we just removed the H from this. Whatever that you have left, it's your conjugate base. I can call this my acid 2 and call this my base 2 or acid 1. You understand? Then we go and analyze the other one. When we analyze the other one, we can see that this guy here, let me quickly work that in a different marker. We can see that the H3, the HCO3. So I have the HCO3 minus, then it becomes what? The H2CO3. So it accepted. A base is a proton acceptor. So now, since this guy is the one that accepted the hydrogen, we call it the base. So remember, when you remove the H plus, you're going to form the conjugate base. When you add the H plus, you're going to form what we call the conjugate acid. What I'm trying to say is that the H2CO3, that's the conjugate acid. So this one is my base. So this will be my base 1 and this will be my acid 2. So ladies and gents, whenever you remove the H plus, you create what? The conjugate base. So for example, I think I can definitely give you something like this. So let's say I give you the HCO3 minus. And now let's say I remove the H. then the new one that I get it will be CO3 2 minus. Where is the H? Gone. So whenever you remove the H, the new product that you get, since you removed, you're going to get the conjugate base. So this guy gave away the H. So since it gave away the H, it becomes what? The acid, because an acid, it's a proton donor. I hope this makes sense. Whenever you add the H plus, you create the conjugate acid. So this will be the acid base pairs, these two. So you just have to give the marker and say that maybe they just wanted to copy this down. You just have to indicate using those lines the very same way I did base 1, A2, A2, B2. And for that, you'll definitely get all that 2 marks. Okay, bless you. Okay, so now let's move to 7.3 and see what we have on this one. 7.3, a lab. Okay, we have a lab assistant was asked to prepare a 200, and look at this. I don't want stress, man. When I work with physics, this is how much I love physical science. So remember, you are in an exam. Some of the things you can definitely forget to do the conventions. So I read the statement, I see centimeter cube. It should be in decimeter cube. So we're going to take this 2.5, divide that by 1,000, which will give us the new volume as what? 2.5 decimeter cube. I convert it, and then we are given the HCl. We have the concentration of the HCl, which is 0.25. So the lab had a bottle of concentrated HCl, which had the following written on the label: the chemical, that's HCl, density 1.2 grams centimeter cube, and then percentage of the hydrochloric by mass in a solution. Guys, I know, let's just assume maybe you don't understand what the statement is saying. There's still a probability for you to collect marks. Okay, so what I'm trying to say is that there's 99% chance that you collected these 4 marks without understanding what is going on the statement. And the best way to do this is to follow the question. What is the question asking? Just use whatever that you are given and the correct formula to find what they are asking for. Calculate the mass of HCl contained in that 250 centimeter cube of 0.25 decimeter cube solution. So you know what you're going to do. Remember, when we calculate mass, there are some certain information that we need to calculate the mass. Look at this. First thing first, you'll go to your formula sheet. You choose the formula that has the following things. Look at this. In fact, just go and look for the formula that has the mass. Remember, you don't know what is going on the question. Well, let me show the 99% chance that you get this right. You go into your formula sheet. Okay, this is my formula sheet. I'm just gonna, let's see. Wow, so there's no formula. Oh, there it is. So I'm going to select the correct formula here. Now, look at how I'm going to select my formula. Did you hear the question saying anything about the what is this? The density. Yes, they did. Let me just quickly confirm. Density, yes, we have, but I don't want to use the density because let's say maybe you forgot about the correct SI unit for density. But I'm going to focus on the formula that doesn't have that, which is this formula. You're going to take this formula, you make the small m subject of the formula. You understand? So this is n, it's equals to m over big M. So it's n, it's equals to m over big M. multiply both sides by big M, multiply both sides by big M. Therefore, the formula for mass is equals to the number of moles multiplied by big M. You see, now you have the formula. This is your formula. The formula will give you direction what you need. So you can say that we need the number of moles of what? The number of moles of HCl. We need the molar mass of HCl. You substitute the 4 marks, it's yours. So the formula will tell you what you need to do. First thing first, we need to calculate the number of moles for that HCl. Okay, so now, how are you going to calculate the number of moles? You're just going to go and say, oh, this is 2.5 decimeter cubed, and that's my concentration. And then what else do you have? I'm sorry, that's your volume. So that's my volume. This is your volume. That's V. Now, 0.25, that's my concentration. So I'm given C and V. You go to your formula sheet, you choose the formula that has both C and V and N because we are looking for the number of moles. You go to formula sheet, the correct formula is this one. You make N subject of the formula. Okay, let's quickly write this down. So to answer this question, the number of moles concentration is equals to N over V. Multiply both sides by V will give us the number of moles to be the concentration times the volume. Just substitute to find the number of moles for hydrochloric acid. You do the substitution. Concentration, you convert. Okay, the concentration is 0.25. And then the volume, you don't substitute 25 now, 2.5, but the 2. You don't do 2,500 by the 2, but you substitute the 2.5. Okay, so this will be 2.5. We're going to multiply the 2 and see what is that equals to. Whatever answer you get will be the number of moles of hydrochloric acid, right, which is what we need now. Let's quickly punch that on the calculator and see what is that equals to. So the 0.25 should be multiplied by the 2.5. This gives us 0.625. That's the number of moles of hydrochloric acid, 0.625 mole. You have the number of moles. We're looking for the molar mass. So we need to look for the molar mass of what? Hydrochloric acid. You use your periodic table to find for H and L. So you go to your periodic table, we can see that the H, the number below H, that's 1. And then you go look for Cl, and the number below Cl, that's 35.5. So the number of moles, the molar mass, is going to be that 1. We add that to 35.5. You add the 2, which is just 36.5. The number of moles, that will be 36.5 grams per mole. Grams per mole. So now you have these two information, you know what to do. I think now you can take it from here. You're going to say the mass from this formula, it's equal to the number of moles, which is what you just calculated as 0.625. This should be multiplied by what? This should be multiplied by the molar mass of 36.5. So let me just rewrite this correctly. Wow. If I'm having so much fun, I can't imagine you on your side, né? So this is a very nice subject. and it's also easy. It's a very nice and easy subject. So the mass will be the number of moles, which is 0.625 multiplied by 36.5. Multiply the two, you'll get your mass. So let me quickly multiply this on my side. 0.625 times 36.5. This gives me 22.8 grams. This is your final answer. So now I think you can see the 99% chance to get this, even if you don't understand the statement. What is going on? Just follow the question, write the formula. The formula will tell you what you need to calculate. First thing first, we know the mass tells us that go find the number of moles for hydrochloric acid, go find the molar mass for hydrochloric acid. Let's work on 3 point. Let's work on that 3 point. 7.3.2. You know, I want us to check if will that work even on this question, where we say this, what is this? Where we say there's 25% chance that, 99% chance to get the question right, even if we don't understand the statement. So we have 50 centimeter cube of, you see, when I see 50, because I know that I might forget to do the conversion, you take this 50, you divide by 1000. This will give us 0.05 decimeter cube. And then this is the volume and the concentration. So this is your volume and this is the concentration of hydrochloric acid. It's used to neutralize 20 centimeter cube. I converted that, which if I convert this, what I get, it's 0.020 decimeter cube of sodium carbonate, 100%. And we have the balanced equation. Calculate concentration of the sodium carbonate. So will this work? The 99% chance. Let's quickly test that. First thing first, if they want the concentration, just write down the formula for concentration down. Remember, the formula for concentration, we say that C is equals to N over V. Okay, ladies and gents, from this formula, I'm just gonna identify what I have and what I should calculate. From this formula, you're going to ask yourself, do you have the volume of, look, come on, please. Look, listen, we are looking for the concentration of what? Carbonate solution. The carbonate solution is N2CO3. Whatever that you do, the volume that you're going to substitute on this formula, it should be for what? It should be for that N2, Na2CO3, which is 0.02. So we have that part. So this will be over the 0.02. Then on top, we don't have the number of moles for what? For that sodium carbonate. The aim is to find the number of moles of sodium carbonate. So now you know what you need to calculate, the number of sodium carbonate. So when you look at this information, we don't have enough information to calculate the number of moles of sodium carbonate. What are you going to do in this situation? You're going to look whatever that is reacting with the sodium, what is this? Carbonate, the sodium carbonate. Sodium carbonate is reacting with HCl, meaning that you'll take the HCl, you calculate the number of moles of HCl, then you use the mole ratio. Okay, number one. you're going to calculate the number of moles for what? For HCl used. Okay, so if we can find the number of moles for HCl, we can definitely use the mole ratio to find the number of moles of that sodium carbonate. Then this is where you can see how easy the question is. 100%. Okay, let me just quickly work this thing out. So for HCl, I need to write down the data. The volume for HCl was given as 50 centimeter cubed, which is something that we converted into 0.050 decimeter cubed. The concentration is given as 0.25 mole per decimeter cubed. Use this information. We know that from this information we can make N subject of the formula the number of moles of that HCl. It will be, we take the two, we multiply them, because the number of moles is C times V, which will give us the concentration, which is 0.25 multiplied by what? The volume, which is 0.050. Let's quickly multiply the two and see what we get. 0.25, it's multiplied by 0.05, which is just 0.0125 mole. So this is the number of moles of what? This is the number of moles of sodium hydrochloric acid. No, I'm sorry. Hydrogen. What is this? HCl. Let me just say HCl. I'm sorry. So now this is 0.0125 mole. This is the number of moles of hydrochloric acid. You have the number of moles of hydrochloric acid. Okay. So what's next? You're going to determine, that was step one. Step two, you're going to use the mole ratio to find the number of moles of that Na2CO3. Okay, so remember the mole ratio, I'm just gonna write this down, is 2:1. So the mole ratio, that's 2 of HCl is to 1 of Na2CO3. Then, therefore, we are looking for what? For the number of moles of this guy. So I'm going to say divide both sides. Let's make this guy subject of the formula. Divide this by 1. Okay, I don't think that will work. Let me not put it like that. Okay, let me not put it like that. Let me just think how I can explain this correctly. So the number of moles of this is twice the number of moles of that Na2CO3. So to find the number of moles of that NaCO3, we'll take the number of moles of hydrochloric acid. Why do I keep saying, okay, hydrochloric, yeah, that's it, divided by 2. That will be the number of moles of this, which will give us the number of moles, which is 0.0125. That's what we just calculated. Divide that guy by 2. The answer that you get, therefore, it will be the number of moles of that Na2CO3. Punch that on the calculator. Just go to your calculator, because already you still have that as your answer, right? Divide that by 2 and see what we get. Okay, so we get a lot of zeros, so this will be 0.00 there are 2 zeros, then 625. After a comma, 2 zeros, then 625. So this will be 0, 0, 0, 625 mole. Wow. I think you can also see how beautiful this is. That's physics, for feet. This is physics. You just have to be creative. Boom. This is what you have, the number of moles. What is the next step? Since you have the number of moles, then the next step is easy. The next step is easy. But now, remember, if you forget to divide the volume, you might substitute it as 20, and this is just wrong. So since we already converted the volume, and then we just go on this equation where there's n, you just put your number of moles, then you'll definitely get your answer. Let's quickly work on that. So C, it's equal to the number of moles over V, which is just 0.0625 divided by the volume of 0.020. Whatever answer you get is going to be the concentration of what? The concentration of that Na2CO3. Divide those two. So I'll go to my my calculator. Let me just take answer divided by 0.02. Answer divided by 0.02. And see what we get. So this gives us 0.3125, which is 0.3 if we round it off, but it will depend on your exam instructions. How should the rounding be? Okay, so let me just leave this as, I'm just gonna round it off to 2 decimal place, which is 0.31. So this is 0.31 mole per decimeter cube. Remember, mole per decimeter cube is your SI unit. Please make sure that you included that on your calculator. And that's it for this question. That's how easy it is for you to collect the marks. Oh, I think we still have that 7.3.3. Wow. Okay, so name a suitable indicator that can be used for this titration. Give a reason for the answer. Okay, let's look at this 7.3. Name a suitable indicator that can be used for this titration. Give a reason for the answer. If you go to the memo, you'll definitely see the answer, and then they'll definitely give a reason, but you don't know where is that answer coming from. So now let me just give you the reason why you come to YouTube to watch how we answer past papers, even though you have memos. So in a memo, you get an answer, but now where is this answer coming from? Okay, so now when we look at this question, my answer is for 7.3.3. My answer is methyl orange. Yeah? So this is methyl orange. But now the reason for methyl orange is because we're going to say a strong acid reacts with what? It reacts with a weak base. Okay, let me quickly explain. Okay, so this is my base. Okay, this is my weak base, this is my strong acid. Let me explain where is this coming from. So this is gonna take 2 minutes of your time, right? So when you look at this, this is how you should approach that question. First, you need to understand the common indicators that we use. Okay, so the first one is methyl orange. Okay, so on methyl orange, we have what we call the pH range. So methyl orange is from 3.1 to 4.4, and then the acid color. The acid color, it will be red, and the alkali color, it will be yellow. This one will be yellow. Listen, we have bromo. This is bromo. Bromothymol blue. So this one, it has the range between 6.0 to 7.6, and then it will be yellow blue. Okay, now this last one, I don't know how to pronounce this one, but for sure you do on your side, né? Even if you don't know how to pronounce it, just know how to write it down. That's simple. Don't stress yourself, né? I don't like, I got the stress, and I don't like stress, né? So you can just learn it on your side. Try how to, you know what? I don't know. Okay, so now when I look at this, né, we have type, we have 4 types. Now we have 4 types of titrations. I'm going to give you all the types so that you can know the type that you are working with. We have 4 types of what? Of acid base titration. So the first one, we call it a strong acid. If you have a strong acid that react with a strong base, you just have to know your table for weak and strong base, which ones are weak and which one are strong. For example, a strong acid, that's hydrochloric. Let's say I have a hydrochloric acid and it reacts with sodium oxide. So we can see that these two, they have an equivalence point of the pH that is close to 7. And then when it's like this, the suitable indicators, I'm going to mark them on the table using green. If the pH is close to 7, you're going to use the methyl orange, bromo, and the last one. The reason for that, these are the indicators that we'll use in this one. The reason is that, remember, the pH, it changes very sharply around 7. So since it changes very sharply around 7, all 3 indicators, they change color within the steep section. So all of these 3 will be for that for that titration, for a strong acid and a strong base. I hope you are with me on that. So let's say that we have the second titration. The second one, it's where you're going to have a strong acid and a weak base. You just have to know your tables, which ones are weak, which one are strong. So a strong acid and a weak base, the one that I can give you, let's say I have a hydrochloric acid, it's always like a strong one that I can think of. Let's say this react with NH3, ammonia. So now, or let's say maybe HCl, it reacts with that one, the one that we have now, the sodium carbonate. You see? So if you look at the sodium carbonate, it's a weak base, right? So the equivalence point for this one, they have the pH that is less than 7. So a suitable indicator for this one, it's the only one for this one, I'm just going to mark that with a different color. So the only one for that one, the one that we're going to use is methyl orange. This is how I got my answer. You just look If I have a strong acid and a weak base, just know that the correct indicator is methyl orange. Okay, so the reason is that the endpoint is in acidic region. So the endpoint, we say that it's in what? Acidic. It's in acidic region. Right. So methyl orange, it changes color between what? It changes color between 3.1 and 4.1, which matches the endpoint. So methyl orange is the one that we're going to use for when we have a titration that is a strong acid and a weak base. So for exam purpose, I'm just going to go through number 3 and number 4 for you guys. So this is how I got my answer on this question. This is why I'm saying the correct answer is methyl orange, because I have a strong acid that reacts with a weak base. So another one, let's say maybe in the upcoming exam, they give you, sometimes they can give you a weak acid that react with a strong base. Okay, so let me just give you CH3, COOH, and then with sodium hydroxide. So now, this one, they have the equivalence point that is the pH that is greater than 7, and then we call them the alkaline. When you do this, the suitable indicator for this is going to be the last one. The last one, remember the one that we don't know how to pronounce, but I know that you know how to pronounce it on your side, which will be this one. So this will be for titration number 3. Okay, so because this guy changes color between 8.3 and 10, so is the one that has a pH that is greater than 7. I hope this makes sense. Let me just give you the last one, then we can end this question here. So the last one, which is, you just have to know only these 4 types. The last one is a weak acid and a weak base. For this one, I'm not gonna waste time. Let's say you have a weak acid like that one that we have on top, and then let's say we have another weak base like ammonia. You see this one, there's no suitable indicator. There will be no common indicator because there's no sharp pH at the endpoint. The pH meter is used instead. For this one, no indicator, no common indicator. And that's it for this one. So if we apply this information to answer that the question, or to explain where I got my answer, this is what you should do. You identify the acid. So the acid, to answer that question, we're going to identify the acid. So this is for that 7.3.3. You identify the acid. HCl, that's your strong acid. And then you identify the base. If you look at the carbon ion, which is the CO3 2-, this one is going to act as a weak, base. And then, therefore, we're going to have a strong acid plus a weak base. This one gives us, we use methyl orange. The reason is that, remember, the endpoint lies in what? The endpoint lies in the acidic region, and methyl orange is going to change color in the acidic pH range. And that's it for this one. So this is just a quick shortcut how to answer that question. I hope you guys had so much fun on this one. This was a very nice question. This question was very friendly, easy 16 marks. My children, my Africa. Let me help you guys out to answer this one very quick. So on this question 8, we have a clean piece of copper, and they say it's placed in a solution of silver nitrate. Okay, the balanced net ionic equation is given. We can see that The first question wants you to define oxidation in terms of electrons transfer. So oxidation, it's loss of electrons, right? So I'm just gonna put my definition here and say oxidation is the loss of electrons. Okay, what type of reaction does copper undergo in this equation? Guys, I know this is 3 marks, but I'm gonna take my time to answer this one. First thing first, you need to write the reaction down, and we can see this is the reaction that we have. So now you choose from oxidation or reduction, then you explain the answer by referring to oxidation numbers. Let's first determine the oxidation numbers for this copper. Let me start with this copper here. I'm gonna do an oxidation number. If you look at this number, it's in free state. Okay, so any element in its free state, it has the oxidation number of what? The oxidation number of 0. So the number of what is this? The oxidation number for the copper, it's equal to 0. Okay, let's work on the copper that is on the right. This one. Okay, so this one, if you look at this, is going to have the number of oxidation. It's ions. That plus 2 plus on top, that will be the number of oxidation. So that will be the oxidation number, it's plus 2. I'm not sure if you get this. So just know that when you determine the oxidation number and it's an ion, you look at the number that you have on top. So if I say for sodium like this, and I say the oxidation number is that plus 1. Okay, so now let's analyze what we have on this information. We can see that when we compare the oxidation number, copper changes from 0 to 1, to plus 2. So the oxidation number increased. Let me tell you something about if the oxidation number increased. Right, so if the oxidation number increased, just note that this is oxidation. We just refer this as what? If this one, if you see that the oxidation number increased, let me write this down. If the oxidation number increased, just note that this is oxidation. Copper will undergo oxidation. So now we can see that the oxidation number of copper increased from 0 to plus 2. Let's link to electron transfer. Now you need to link to electron transfer. I know that already I said the correct answer is oxidation, but let me help you how you can link to the set. Let's link to what is this? Oxidation. Link to electron transfer. So look at copper. The copper, it loses 2 electrons. I'm not sure if you understand. So since the copper, we can write copper like this when we link this to electron transfer. So the copper becomes Cu 2 plus, then plus 2E. This tells you that copper will lose loss of electrons. So for the fact that we start with 0, then we end with plus 2, you're going to put the plus 2 on your reactants. I'm sorry, on your products. Since it is on your products, this tells you that there was loss of electrons. And then since it's loss of electrons, that will be oxidation. So what we're going to do is that the correct answer is oxidation. And when they say explain your answer, we're going to say the oxidation number of copper increased from what? it increased from 0 to +2, meaning copper loses 2 electrons. I hope this makes sense. The next question, 8.2. Sulfur dioxide gas is a bubbled into acidified solution of potassium perma. What is this now? I remember this weight when I was teaching the grade 12 when we're doing I don't remember what was that molecule there. Perma, I don't know. I don't want to lie. I don't know how to pronounce this, but definitely I know how to write it down. That is what is important. You know, like, I don't know, guys, but if you are in grade 11, there's this life science terminologies, like there are some terms in life science, yes, you can't even pronounce, but the best thing is to know how to write those names down. Okay, so this we can see gas SO2 sulfur oxide going inside, and then okay, this is the one that we have the solution inside. Okay, so this guy here, this is potassium. You see this weight is potassium, and that's the molecular formula for that. KMnO4. Right. So now it is observed that the solution turns from purple to colorless due to the reduction of Mn to O4 to minus ions, what. During the reaction, SO2 is oxidized to sulfate ions. Determine the oxidation number of magnesium in the perma. Let me not force to call this weight, this part here, and let's say it's permanganate. Maybe it's permanganate, I don't know, but you'll definitely if I got that one right, you can tell me on the comments. I'm just gonna go with permanganate. Okay, so now they're saying they want us to determine the oxidation number. Okay, so I'm going to take this step by step. I need you to first start by assigning the known oxidation number. So I know that in that Mn, let's say in MnO4 minus. Okay, so the MnO4 minus. So if I have this MnO4 minus, I know that from this guy, oxygen usually has an oxidation number of what? You see in this, oxygen will have an oxidation number of 4. I mean minus 2. So the O will have an oxidation number of minus 2. And therefore, you can see that there are 4 of them. There are 4 of them. Therefore, if there are 4 of them, the total contribution from oxygen will be 4 times that minus 2, which is equal to minus 8. Guys, if you don't understand where the minus 2 is coming from, these are the laws of oxidation numbers. So oxygen will always have minus 2 in that one, okay? And then this is minus 8. So we're going to let the oxidation of the number of magnesium to be X. So the number of magnesium, the oxidation number of magnesium, this part here, I'm going to let this guy to be X. So this will be my X. So we're going to use what we call the overall charge. The overall charge on the ion, if we look at this, the overall charge is what? The overall charge is it's minus 1. Okay, which is this one on top. So the overall charge, see now, overall charge, that will be it's minus 1. Okay, so this tells you that if we take that X, we add that with minus 8, we should get an answer of minus 1. then you solve for x. So when you solve for x, you have x minus 8, that's equal to minus 1. Therefore, x is equal to the minus 8 comes to the other side to be positive. That will be minus 1 plus 8. The final answer of x is 1. The final answer of x is plus 7. So the oxidation number, this tells you that the oxidation number, okay, of that MnO4 minus is equals to plus 7. And that's your answer, you are done. Okay, so maybe if let's say that maybe someone will prefer to use let me do this. Let's say that maybe someone will prefer to use this one, the one that is given here. You take this guy here, you see this guy. Let's work with that one. Let's see if we get the same answer. So we're gonna say in MnO for 2 minus. We know that the oxidation number for oxygen is minus 2. So since it's minus 2, there are 4 of them, as you can see, O4. Then this will be 4, you multiply that by that minus 2, we get minus 8. Then the overall charge for that one, it won't be minus 1. Remember, the ion is 2, it's minus 2. So the overall charge is just minus 2. So meaning, when we take that x, remember we let the oxidation number of magnets to be x. When we take the x, we add that with minus 8. We should get an answer of minus 2. So therefore, and then x minus 8 is equal to minus 2. Therefore, x will be a minus 2 plus 8. So this tells you that this will be, what is this equals to? So this will be x, it's minus, positive 6. So the oxidation number in this is going to be 6, and the oxidation number in that is going to be 7. If you give them one of this, you are still correct. It's up to you which one you're gonna give it to them. Both of these answers are acceptable. You can definitely give it to them and collect all the marks. Do not double this marks and give it to the next person. These are your marks. You definitely deserve this marks. This is just easy 7 marks. And that's it for this one. Okay, yeah, that's it for this one. Permanganate. I hope I'm saying this right, né? Yeah, that's it for this one. All right, so this is where I'm just gonna stop for the lesson. Guys, if you really enjoyed the lesson, please make sure that you share this lesson with your classmates. Help them not to double the marks and give it to the next person, but they should collect these marks. Please make sure that you call your classmates. Let's massify them with these easy marks. And hopefully, guys, I'll see you on our next lesson where we'll be preparing for trial exam. So now that you are writing your paper 2 exam, the next lessons will be focused on your trial exam preparation, which is also part of your final exam preparation. If you just join in the lesson now, or is the first time you see this kind of lessons, my lessons on YouTube, make sure that you subscribe to the channel, join the family, and I'll definitely make sure that you feel at home. Sharp.